Paris BUTTFIELD-ADDISON. He is a great guy because he not only co-founder of Secret Lab at game development studio based in Australia, but he wrote something like 20 different guides book on machine learning and game development. And he is gonna give us a very good Q&A session. However, in the meantime, the video will be recorded because it's gonna show us high definition images, and we want only the best for you here. So let's start with the presentation.
Hi everyone, this is simulating your robot brain with a game engine. My name is Paris. You can find me on Twitter at ParisBA. Feel free to tweet me at any time. And you can visit my website for slides and other resources about this talk later on. I'm primarily a video game developer, but I do a bit of research. I do all sorts of things really. I'm also well known for writing a lot of books on AI with Swift and things like that. And we're currently working on a book on the topic of this talk. I'm speaking to you from Hobart, which is in Tasmania in Australia. It's the little island down the bottom of Australia. It's a really beautiful place. It looks kind of like this. You should definitely visit sometime when that's permissible. I'm here to talk about simulating your own robot brain. For example, the brain in a self-driving car. And doing that using a game engine. Game engines are really cool and really useful for all sorts of stuff that is not a video game. And I'm hoping you'll take that away from this talk today. This talk really involves two specific things. One thing is machine learning, and the other thing is video game engines. These two topics are really dear to me in a variety of ways, and hopefully they'll become dear to you as well. Over the last few years, AI has exploded in all sorts of ways. All kinds of AI things have popped up. From AlphaGo, for solving the specialized cognitive challenges of the board game Go, to DeepMind's AI learning to walk, to things like VizDoom, where they've taught an AI to play an old video game purely based on the visual screen input of the video game. There are lots of problems to be solved using AI and machine learning, as you know. They're rich, complex problems, and some of these problems might benefit from a physical or a visual simulation element. AI is increasingly focusing on problems that are either cognitive, physical, or visual, or some combination thereof. For example, AlphaGo's learning the strategy of Go is a very cognitive-focused problem. DeepMind's walking AI is physical, with procedural animations teaching critters how to walk, and VizDoom is purely visual, because it learns to play Doom from looking at the computer screen. Combining these three domains produces really interesting results, and that's where game engines come in. So, the two pieces of technology I'm going to talk about today are primarily Unity, the popular video game engine, which is about 60%, depending on how you count, of the entire video game industry. It's a really powerful video game engine that can be used for everything from games to film VFX and everything in between. And it's the software that me and my colleagues do most of our day-to-day work in. The other component we're using is PiTorch. We probably don't need to explain PiTorch. Suffice it to say, it's one of the effectively two dominant machine learning frameworks in the world. The Unity game engine, which for the most of its life was just a game engine, heralded its move into this space with the release of a paper where they argued that 3D physics simulations, as used in video games, were a really good platform for generalized or general artificial intelligence. This is a really good paper, and if you get time, you should check this out. It's a really good summary of why video game engines are a good place to do AI. Anyone here who has done much ML or ML research would know that a long defining point or moment in AI research is that everything has to be custom designed and targeted for each application of the technology. So the idea of a general AI that works for kind of everything is a really big deal. Generalized AI is kind of the idea that one big framework or one engine, one piece of software could do everything. And Unity is kind of positioning itself as maybe that piece of software. It's a bold claim. With this paper, Unity released an open source plugin for their engine called Unity ML Agents Toolkit that allows environments made within the Unity engine to be connected to PiTorch and to TensorFlow and interact with the simulation and the machine learning toolkits. That's what we're going to be looking at today. Unity in particular is pushing very heavily into the area of AI known as reinforcement learning, which is apt given the conference's name. So we're going to have a quick run through of what this means, reinforcement learning, in the context of a game engine, and why it could be regarded as a generalized solution. In reinforcement learning using Unity or any game engine, there's an agent or multiple agents. That agent exists in the environment. The environment could be anything. It could be a chessboard, it could be a fully realized first-person shooter type game, it could be literally anything. In this environment, the agent makes some sort of observations that enable it to perceive the environment. Those observations could be measurements or a literal camera in the environment or anything in between. A decision-making system, in Unity this is referred to as a brain, receives the observations about the environment and makes a decision, sending that back to the agent. The agent then executes this decision, and the agent and the brain are then rewarded or penalized based on some sort of policy. And in the training phase, this is how you arrive upon a policy, and in the inference phase, this is how you enact the policy. During training, decisions start relatively random, and as the brain is trained using reward signals, it's guided towards a good optimal policy. An optimal policy in this case is just a nice way of saying the reward signals make the brain get the agent to do the thing we want the agent to do. So the three key parts, as far as we're concerned, are the actions, the observations, and the rewards. Actions are changes in the agent's configuration, so typically moving or doing something. Observations are what the agent can measure about its environment. These are often things like distance to a certain type of object, or a ray that is cast out in a certain direction, which tells it how far it needs to travel to get somewhere. Rewards are basically points that guide it towards a good policy, or negatives. Rewards can also be negative. By default, Unity recommends using an algorithm called proximal policy optimization. They present this as kind of a catch-all AI algorithm. It's not really that, but in many cases it can be treated like that. PPO, proximal policy optimization, basically tries to turn everything into an optimization problem and applies a simple policy to iteratively improve whatever it's doing. It's mostly fine to treat this as a bit of a black box if you don't know or can't be bothered working out how to tweak it, but if you understand it, you can tweak it, and that's one of the beauties of this system. We're going to hand wave over this a little bit today because as far as using this with Unity is concerned, PPO, proximal policy optimization, is an algorithm that's implemented on the PiTorch side of the equation, which means you can just say, I would like to use PPO, please, and it kind of goes and does its thing. If you are comfortable with PiTorch or TensorFlow, Unity supports both of those frameworks, you can control and tweak PPO and the specific implementation details in there. Unity has written really good wrappers around the Python components that basically mean you can just say, I would like to start training, please. I would like to start inferring, please, and you don't really have to think about it. It's quite useful. Okay, before we can start looking at understanding how this actually comes together, you need to understand a little bit about Unity. I'm assuming most of you are probably ML people rather than game developers, so I'm going to give you a little bit of rundown of the basics of using Unity. Unity is great for building environments for all sorts of things. And building an environment for a machine learning problem is basically the same as building a game. So here's the basic concepts of Unity. A world in Unity is comprised of one or more scenes. A scene is basically an infinite empty world that you can put things into. In this case, we've made a scene and put a flat plane in it. It's actually a squashed cube. In a scene, you populate it with game objects. A game object can, but does not have to, represent a physical object. So a game object can be a thing that has a physical presence in the game world or does not. Game objects can be literally anything you could think of. Floors, cubes, walls, sound effects, cameras, lights, things that make noises or emit particles, or things that just control a script that actually don't have a physical presence at all. A game object in Unity, which is the thing that makes up your scenes, is made up of components. Components are both data and functionality. So things in your game are composed out of multiple components which make up one game object. All game objects have at least a position, a rotation, and a scale, which is a component, but they usually have others as well. The other thing you need to know about is an asset. An asset is pretty much anything the game knows about. Things like scripts, textures, materials which say how things should look in the game, 3D model files, neural network files, things like that. They're all assets in Unity terminology. Most components are assets until they're added onto a game object, when they become a component that refers to an asset. Okay, so that's a really, really quick understanding of Unity. Let's have a look at the Unity ML Agents Toolkit. Again, there are two main parts here that you need to know about: brains and agents. Brains and agents fit together a bit like this. There is only one brain in most scenarios, which is the thing that learns a policy to do something and then enacts that policy with the agents. That brain is often hooked up to multiple agents, which all do the same thing. Each agent will generate a bunch of observations and send them to the brain. The brain and the agent will work together to perform actions based on a policy, and the brain will then assign rewards to those agents. When it's learning, the brain will learn that when it receives certain observations and follow up with certain actions, it gets positive points, positive rewards. And when it gets negative rewards, it will learn those as well. And this is where it can infer what was good or what was bad. An untrained brain here would just enact random actions. So here's a little map of how it maps to the pieces of technology we're using. Our agents exist within a virtual environment, which is what is generating in observations to send to the brain. During training, the brain itself is deferring its judgment to a running PiTorch process that's managing the neural net as it learns through an inter-process bridge. So Python's running, Unity's running, they're talking to each other. And then once the training is done, the neural net is locked in and it's baked into a file, which can then be used without the bridge for further inference in Unity, where you can use the trained model to make your agent do stuff. Let's do a quick demo inside Unity itself. I'm going to switch to some Unity. So in this example, we've built a small robot, which is this thing right here. It's really cute. It's a little car, runs around. The goal of this environment is to teach the robot to push the cube, which is this thing, into the goal area, which is this thing. Okay, it's a pretty simple goal. It needs to push a cube into the right place. It's kind of a sorting robot. So the robot's action abilities are movement. The robot can move in one of 4 directions for each single step of a simulation that it runs in. So by altering direction between the steps, it can also go diagonally, but it actually only really has 4 directions it can go. Its ability to go diagonal is a side effect of its having 4 directions very fast. There's a physics simulation happening because Unity is a full game engine that simulates physics, which means if the robot pushes into a crate, the crate will slide along with the robot and you can push it around. So robot can move in 4 different directions. The observations for our little robot are that it has 14 different ray casts. Okay, a ray cast is like a perfect laser beam that can measure how far away it is from something. The robot sends 7 ray casts from the middle of its body, as you can see here, out at a variety of angles. Okay, and it sends another 7 from the same angles, slightly above. So you can see them here. This sort of covers the entirety of the height of the area that it works in. These raycasts provide observations regarding how far away and where the walls are, where the crate is, and things like that. Here's a little bit of a clearer view. Okay, so rewards. When the agent pushes the crate into the goal area, it gets a large reward. It's done a really good job. It also gets a small negative reward. We still call it a reward just because that's convention. It gets a small negative reward for moving at all. So every time it moves at all, it gets a very small negative. This small negative for moving intends it to make it economize its movement. So it should move as little as possible in order to accomplish its goal. Basically, we want it to push the crate into the goal using the fewest possible moves. When we build an environment like this, we need to test it. So what we do is we run the simulation at ultra high speed, letting the agent take random actions and writing out the neural network file with weights influenced by the rewards given for the random actions. The training process involves using the Unity ML Agents Toolkit command line tools to connect to PiTorch or TensorFlow and Unity. The training process can be monitored using this tool's output, and you can look at the average rewards and losses changing over time. But if you're into machine learning, you probably know that there are better tools, and one of our favorites is TensorBoard. You can use TensorBoard to monitor your agent's successes or its failures. And because it's just Python under there, you can pretty much use any analysis tool that supports TensorFlow or PiTorch, and there's a lot of them, but TensorBoard's a pretty good, simple and easy to use one. With TensorBoard running, this basically means you get lots of graphs showing the cumulative and average and current rewards for your agent. So, when you've trained, you end up with a robot that hopefully works. This is my little robot sorting cubes. As you can see, he does a pretty passable job in my opinion. Look at him go. He kind of gets behind it and slides it around and does a reasonably good job of sorting. I'll actually turn on the raycast view in a second. So you can see, so there it is. You can see that the raycasts are coming out of the robot, which are the flickering green lines, which are sometimes a little bit hard to see, showing you the raycast that the robot is using to sense its environment. It's just a visual representation of the beams that the robot is using to navigate. You can see he does a pretty damn good job, and this is pretty impressive. And this was trained in about 10 minutes using the exact reward scheme I showed you a moment ago. And the code for this is available on my website, and there'll be a link at the end, so you can go and play with this yourself if you'd like. It's pretty straightforward. I think this is a very impressive demonstration for a couple of minutes of training. Okay, so next thing I'm going to show you is a race track showing a very simple self-driving car to show how quickly behaviors emerge. This car taught itself to drive. Admittedly, it's a little bit wobbly, but it's still fairly impressive, around a very simple track in about 4 or 5 minutes. It gets rewarded for not hitting barriers, and it gets rewarded for progressing further around the track and completing full laps. So as you can see, it's a little bit hesitant, but it overall does the job of driving around this track fairly well. And this car is using a different kind of sensing scheme to the robot you saw. And what I'm going to show you is how that works. So the car's observation in this case is actually a forward-facing camera. And the neural network has no other observations. It doesn't have any raycasts. It has a single camera mounted to the front of the car. And you can see the camera here. This is the camera that the car uses to train. The neural network is learning based on the images received from this camera and learning to navigate the course based on the penalties and rewards also given to it. So it's given the same rewards and penalties I mentioned. If it hits a barrier, it gets a negative. If it successfully completes a lap, it gets a positive. If it goes forward, it gets a small positive. And that's it. And its inputs are the picture. It does not have any rays. So this is acting more like a human driving than anything else. And this is a pretty good attempt at driving. This is built into Unity. So all you need to do is say, this camera is an observation. You don't need to do anything else. It just magically works. And all the convolutional neural network stuff that is happening under the hood just happens automatically for you. So this is a really good way of showing people the power of machine learning very quickly without having to hook up something complicated. I think this is a really good demo, and you can use as many cameras as you like. So any visual problem can be very quickly hooked up and tested. And I think this is a great way of doing that. There's lots of fabulous demos in Unity's ML Agents Toolkit examples, and I highly recommend checking out those demos. One of my favorites is this humanoid, which teaches itself to walk. This is not animated. This is a whole bunch of joints with different weightings on the rewards, and it's rewarded for staying upright and moving forward without falling over. If it touches the ground, it loses points and things like that. This is really cool. This is learned to walk in maybe an hour of training with fairly minimal code. So if you need to build something in a game engine that needs to walk, you know how to make a horrifying human. But most of the reinforcement learning that you do in Unity ML Agents boils down to this cycle. It's pretty standard reinforcement learning. A policy is formed, saved to the brain's trained neural network, and the reward signals are in there, and then it just goes back and forth between those. There is another way you can do it with Unity though. Behavioral cloning, which learns from human-provided demonstrations instead of reward signals, and all sorts of combinations. You can even do curriculum learning, where you have a whole bunch of stages that something needs to go through to get to an endpoint, and you use the various stages to build up levels of knowledge. You can also use multi-agents, where you require things to work together to achieve a goal, or have varying sequential objectives. Let's take another look at one final demo. This is a car we built trained with behavioral cloning. So a human is driven around this track using keyboard controls for about 15 minutes, using the keyboard, so no ML, and the recording of that has been given to the computer. Not the video recording, the keyboard control recording and the observations from some raycasts the car has on it. And then using those as signals instead of rewards, a policy has been formed. And this has only taken about 15 minutes of driving and then maybe a minute of training. As you can see, this is actually pretty good for maybe a minute of training. So this is a totally different way of doing things though. No reward signals are used here, only a human provided demonstration of how to drive, as well as the raycasts. I think this shows that you can create some pretty convincing human-like behavior very quickly. Obviously, Unity would like you to use this for everything from AI in video games to creating like pick and place robots for the real world. That's all the demos we have time for today though, and hopefully at this point you're wondering, so what? What is the point of all this? It's hard to say what a generalized AI solution like this is good for, and it's generally hard to summarize why AI is good at all on one slide, but this shows the potential for a great range of applications, simply because you can visually, spatially map out problems, simulate and test them, and you can even figure out if your problems are even necessarily visual or spatial in nature. And you can solve them in an interesting way that's easy to visualize, easy to demonstrate, and easy to enthuse people about. It's also really easy to iterate on this because you can add more things to your environment and test it and evolve it as you go. That's just plain fun. Unity is really powerful and has a lot of tools to build really complicated worlds. So there's nothing stopping you from building something that has thousands and thousands of moving, intelligent pieces and then testing something inside it that requires that level of fidelity to the real world. So if you've ever looked at things like Amazon's Deep Racer, where you train a machine learning model and then put it in a physical toy car, Unity is fully capable of doing that, but on a much grander scale. And there's packages that supports pick and place robots that really exist that you can buy. So you can train and build your model in Unity and test it, and then transpose it to a real robot. And there's all sorts of other things you can build, ranging from tools that let you synthesize data to tools that let you simulate really complicated beings like walking bipedal robots and things like that. Highly recommend you check it out. I've put a little getting started guide on this website for you. I hope you really enjoyed this talk. This is me at Reinforce 2019 in Budapest. We hope to be back in person next time. My wife and I spoke there. It was amazing. Please message me if you have any questions. I think I'll be answering questions right now as well. And yeah, thank you for watching.
What a cool deep dive. Hello, Paris. Welcome. It's nice to see you.
Hi.
So we have already a bunch of questions for you, but before I want to remind the audience that they should vote for you on the poll because you deserve some few stars, quite a few, and to write more questions if they want, because we do have 15 minutes, so you have the time to ask. I will start straight ahead, if you don't mind. The first question is from Peter, and he says, is it possible to modify the observer configuration? For example, CNN architecture for site observer. Very technical question.
Yeah, absolutely. So you can change absolutely any aspect of how the observer is receiving images from the game engine and what it's doing with them. So if you wanted to create a completely custom neural network on the observation side and implement that in Python, you can connect that to Unity, no problem. The magic of using something like this is you effectively have a Python bridge to the game engine, which means you can make the game engine do whatever you like. And the Python side can also accordingly do whatever you like, and they just talk to each other over that bridge. So if you had a very specific set of things you needed to do with the images for your some sort of custom site observation on the Python side, you could connect that no problem, and you would just receive images. Some of the things we've done are connect like a Jupyter notebook and receive still images very occasionally from Unity and look at those, and those can be pulled into the Jupyter notebook in real time and analyzed. So it's very powerful and very flexible. So yes, you can customize the observer configuration and plug in your own CNN if you wanted to.
Yeah, possibilities can be thousands, I say.
Yeah.
Actually, I will move on now because we have Laszlo, which is asking about randomization. He's asking how easy it is to randomize the environment for more general learning. So it's like, for instance, if I want to keep track of a car, do I have to build the different tracks? Can it be randomized and whatnot?
Absolutely. So you can randomize whatever you like. The framework that Unity has built supports what they call environment randomization, where you can set specific parameters that are then randomized each run or each cycle or each instance. And those are things where you can very specifically define in Unity, this object gets randomized each time. So it might have a random position, color, size, scale, and things like that. So not only does the ML side of the environment support randomizing parameters for different components of the simulation, but also because it's a game engine, you can create your own randomization. So every time a track is spawned or created into the world, you could make it generate a different configuration for itself, completely separate from the ML. So both Unity itself makes it very easy to randomize parameters to your liking of the world, as well as the ML agent system can randomize those parameters. And because the ML agent system can understand those parameters can be randomized, it's possible to give the context of what has been randomized or what has been changed to the ML system if it needed it. So yes, you can absolutely do that. And that's highly recommended how you would use this. You would randomize the track regularly. Yes.
Okay. What about instead what Orshoya is commenting on? So, okay, first of all, she says, great presentation. I agree with her, so I should say. When do you see this technology implemented? So in FPS gaming, where the both characters starts acting like this, or when, in what applications?
There's a lot of great places to implement this. I think because it comes from the world of game engines, people often naturally assume it's going to be useful for building a character for a video game, and that's definitely true. But I think it goes beyond that in terms of your ability to test out ideas before you have to build them in the real world. So for example, if you were building a real life physical robot for a warehouse and you wanted to explore the possibilities of that robot, you could build a realistic model of that robot in that it had all the same joints and connections and movement abilities of the real robot that you were planning to build in Unity. And because it's much cheaper to build a virtual robot than it is to build a physical robot, you could experiment with how you were going to train that robot brain and how it was going to work and how it was going to pick up objects from, for example, a warehouse floor and move them around before you even did a single element of physical robot design and construction. And by doing that, you've saved a lot of money, you've saved a lot of time, and you've been able to experiment and iterate with your robot much cheaper and much more effectively. And then you can use it there. But there's hundreds of applications. Anything that you might need to build an AI for that has a visual or a physical component, you could do it in a game engine before you did it in the real world.
So you're saying this is a game changer. Cheap simulation, we can even risk life, they are fake life.
Yeah, I think it's really useful because I think there's so much that needs a physical component, whether it's a camera mounted in the real world looking at something or something that actually has to move. And it's much easier to do it virtually before you do it physically.
I agree with you. This is open to many possibilities. What else? We have here Gerald, probably. I did not ask his question. Yes. How long does it take to make a small game? So the racetrack example for someone with moderate experience in Unity.
So if you're reasonably confident with Unity or have done a couple of days of tutorials, it's very quick to make a game in Unity. The racetrack, I think we put that together in maybe 2 days. It's very simple. It's just a racetrack. There's not much to it. As you can see, it used fairly simple low poly geometry and was designed to look like a racetrack, but be pretty simple. So I think it's very, very quick to make an environment. Once you have got the handle on how Unity works, you can assemble pretty much anything as long as you don't mind it looks good. If it looks good, quickly. Making something look really pretty and really like a real video game is hard and complicated. Making something that looks good enough to test an AI idea is very quick.
Yeah, of course. We did with my nephew. He's like 10 years old. We did a video game in one afternoon. He was like so into it. So I see your point. Like the basic stuff are there, and it's other things that are complicated. The features. It's
really important not to get carried away with the looks, because you can make something that simulates enough of the facets of the real world quickly. And if you approach it from the perspective of it's a video game, it's very tempting to focus on how it looks, when realistically you can assemble something that simulates something you want to test out of cubes. So yeah.
Yeah, and who cares about the pretty things? Okay, let's move on because we have so many questions. So how successfully, this is from Laszlo.
Yep.
How successfully could a model be trained in a game engine and then be applied in reality? So what is the accuracy, I guess it's the questions. Does the game engine represent the real world in case of a robotic application, for instance?
Yes. So if you think of like a pick and place robot, so like the robot you saw at the end there, like a hand that picks things up, they are very precise in terms of their abilities. So I'm not a robotics engineer, I'm a game developer primarily. But as it turns out, robots, when they sell them, they very specifically define their range of movement. So we know exactly to like within a tolerance of like 0.01 millimeters, exactly how far every single joint of a robot arm can move. And because we know all the constraints are very precise, when we implement that simulated robot in a game engine, we can say it has exactly the same set of constraints as the real robot. And the game engine is completely accurate enough to do that down to the same level of precision as the real robot. So you can very much transpose what you've done into the physical world very easily if you are aware of the constraints of what it is you are building in the physical world. Obviously, the self-driving car you saw in my two examples is nowhere near as complicated and doesn't exist in anywhere near as complicated a world as a real self-driving car. But it gives you an example of how you can start breaking down a problem piece by piece and at least conceptually understand things. So I think one of the things that this is helpful for, if you do not want to even simulate all of the real world and then transfer the brain from the game engine into the real world, it can at very least help you break down a problem or visualize a problem that you are trying to solve with a real world object and break it down into simple components that you can look at. Because when you see that car moving around a track, you can start thinking about the potential ML problems of making a real car navigate a track in a whole new way just by having that visualization there.
Sure, sure. See your point. Let's break it and make it. Tamas also asked about whether do you see any non-physics problem that can be also simulated here? So are we only talking about physical fake words, or is there anything else you can do?
You could definitely simulate non-physical problems. I think the game engine naturally lends itself to physical problems just because it has a physics engine that is very accurate. But anything that has a spatial or visual problem can be simulated. So if you think back to like I mentioned at the very beginning, AlphaGo, trying to solve the Go board game, you could solve simple placement problems. So I'm not sure what the game is called around the world, but in Australia we call it like noughts and crosses or tic-tac-toe with the crosses and the circles. Games like that where you point a camera down at a board and then use image understanding learning to understand the position of things. You could build a virtual implementation of this noughts and crosses game in Unity and then point the camera in the game engine at the board and then train a neural network to understand how to play that and move it around. So I don't think that's essentially a physics problem. I think it's more of a cognitive problem, but because you've built a physical representation of it, it becomes a visual problem that you can then solve using cognitive processes.
It's probably what you were also mentioning about having collaborative robots or these kind of things. It's very fitting, I guess. So yeah, not only physics. Let me see. I have so many questions popping up for you. Peter is asking about this brain. If this brain that you're talking about, they always mention only one brain. If you can have more, and if they can be combined. So could these brain models put together? And for example, a model for picking things with a hand, then you put it with a leg and whatnot. Okay, so it's...
So that's a fabulous question, and that's not one we actually get asked very often. So it's a great question, Peter. Thank you. That's called multi-agent learning. And it's even if, for example, a demonstration we often do with this technology is we build, and this is often more for children, we do like presentations for children to try and enthuse them about science and technology. And one of the ones we do is we build sort of a big spider robot. So it looks like a spider and it walks around. I don't use it in presentations because enough people are scared of spiders and it moves enough like a real spider that a lot of people get scared by looking at it. So we have a robot spider that walks around and it has a brain that controls its walking. So it taught itself to walk based on reinforcement learning signals and it sort of walks around the landscape like a spider robot. But it also has a little gun on its head, which it uses to shoot cubes out of the environment it lives in. And the gun on its head is actually a separate brain to the brain that controls its legs. So they don't actually talk to each other. So the way it works in the simulation context is there is a brain or a neural network model that controls the walking and has learned to walk. And that brain is trying to walk towards any cubes that it detects in the environment using its sensors. Then there is a separate gun brain attached to the gun on the head, which can rotate the gun and fire the gun. And that brain is trying to rotate the gun to point it at a cube and fire at the cube to destroy it. They do not actually know about each other's existence or talk to each other. The gun just knows its position in the world, and the robot, the brain that controls the moving of the robot just knows its position in the world and that it needs to move around. And because they kind of end up working cooperatively, it looks uncannily intelligent. So it looks terrifying because this robot charges around the world very quickly and destroys things. But they don't know about each other. So it's called multi-agent learning because technically there are two agents there. One is the gun and one is the moving robot. But as far as the entity in the game simulation goes, it's one entity. So if you're willing to break your problem down into multiple entities and do multi-agent learning, you can achieve all sorts of interesting things.
I guess this has some limitations since you are putting together components that are not used at interacting, right? So there are new states that you cannot... But
yeah, you could also explicitly share information between them if you wanted to. We just chose not to in that example. Yeah.
Okay, cool. Let me see. I have here now Nora asking you. Can you elaborate a little how transition makes from Unity world to real world within a trained network at a robot? So how do you move from the simulation, I guess, to the real thing after you've done the simulation and the training?
So when you've done the simulation, you end up with a very standard ONNX file, or whatever it's called. The file that you get out from like PiTorch or TensorFlow is a very standardized weighted model these days that is a very familiar format to most machine learning people. I do not think anyone who has dealt with machine learning will have trouble transposing a model that we are generating with something like this, which is just a series of weights into any other environment that uses some sort of Python machine learning framework. So really all you're doing, it's as simple as saying when you have trained something using the game and the simulation, you will end up with a neural network file that is a perfectly reasonable thing for you to read in using any inference engine like TensorFlow or PiTorch or things like that. One thing I didn't mention, I kind of glossed this over in the presentation, is that when you are doing this with Unity, the training is doing training with either PiTorch or TensorFlow over that Python bridge. But when Unity is running inference, so when you're just running your robot, Unity actually has its own inference engine inside the game engine called the Unity Inference Engine. And they've done that because when you want to ship a product using Unity, your binary doesn't need to ship TensorFlow or PyTorch with it, it just ships Unity. But you can do inference using PyTorch or TensorFlow if you wanted to, and then apply that anywhere.
Maybe on that, is there any difference in timing or performance between the two solutions?
Not that I know of, but there probably are minor differences, yes.
Okay. Let me see. We have now Gerald. He asks you, do you have any best practice for defining a reward strategy, I presume, in this field? And if you do experiment tuning, if yes, what kind of diagnostic do you look at, and so on?
There is no best practice for defining a reward strategy. It's basically trial and error until you find one that works really well. Tuning involves looking at your mean reward and your mean standard of reward and seeing whether it's going up and whether your agent is doing what you expect it to do. And as with some areas of machine learning, it's very much more art than it's science in a lot of ways, in that you just end up tuning the numbers until you get something that behaves the way you want it to. The whole objective is to usually make something behave in a way that you want it to. So when you are tuning, you are usually looking for a very particular behavior change, and it's often quite obvious very quickly if it's going to do something completely wrong. Humans are not necessarily very good at intuiting the correct reward structure for the model, so it very much is often a case of just trial and error until you make it work.
And you have a beautiful visual feedback.
Yeah.
So
it turns out it's a lot easier to tune numbers for a machine learning simulation when you have a visual to go with it. Yes.
I mean, I can imagine when you have 20, 30 different numbers to look at, It's not the same as looking at an image of the
Yeah.
robot like you showed. It was a very
Yep.
powerful example you gave us. Let me see what Jolt is saying is it possible to create a brain that learns in production, do you think, with Unity?
Yes, you can create a brain that learns in production. You can also, as with many machine learning frameworks, you can define certain paths in your model as updatable and update only those paths based on new information. So, for example, if you taught a robot to walk using one particular brain or one particular model or one particular part of your model, and you didn't want it to improve or change its walking behavior later on, you would mark those particular parts of the model as non-updatable. But the model might also have a component where, in addition to walking, the robot needs to identify certain objects in its world. And in production, you would then allow those paths that rely on work for object identification to be updated based on new potential objects it could understand. So its walking behavior would then not change, but you would increase its learning on identifying objects in production by updating those paths.
Well, this is, again, lots of potentialities I see here.
Yeah.
So actually, I think we ran out of questions. So maybe I would like to ask you, in production, in your own experience with your startup, what is the current usage of machine learning that you have on a daily basis? Is it
all sorts of things? Yeah, all sorts of things. So for everything, we primarily build video games. So we're definitely experimenting with using this technology for creating AI in video games. I think that's still very early though. And there's a lot of usage in science. So scientists who need to simulate something, work with teams like us to build a environment that sort of represents whatever their problem space is and run a simulation in that. And I think it ends up being a really good way to test things, as I said.
Yeah.
So it's mostly scientific.
I see, I understand. Also, there is Marcel with another question for you. So we cannot still let you go. But I lost it. Where are you, Marcel? He was asking about imitation learning with ML Agents Toolkit. If you can probably tell us something.
So yeah, imitation learning is a broad field of stuff that you can do. When you do imitation learning, you can actually hook up the thing you have made inside the game engine to some sort of human input. And in that case, instead of providing hints towards what you want it to do based on with rewards, you provide hints towards what you want it to do based on the input of the human. So the very last example I showed you where there was like a purple car driving around the track, that was trained with imitation learning, where I spent 15 minutes driving that car around a track using the keyboard controls on my computer. And then I ran a training cycle with that providing the input to the simulation. And through that, it was able to learn a policy to drive like I did, and presumably making the assumption that hitting a barrier was bad and going forward was good. And we got there and it did that. And there are a variety of ways you can do that with Unity. There is very simple behavioral cloning where you can provide a demonstration recording or demonstration recordings, and it will learn from that. Or what you would actually do in production is you would use a human demonstration to start the process, and then once you've started the process, you would move to pure reinforcement learning and continue the process with reward signals. So you combine imitation and reinforcement.
Okay, it was exhaustive, I have to say. Maybe I can ask you another question before we run out of time, because I think Laszlo is building up his previous topic. He's asking you, what about the observation space change? So when we go from simulation to real environment, for instance, we would have different objects and camera images than what was in reality in the game.
Right.
So
that's a great question. Thanks, Laszlo. So the way this is typically handled is when you think about a self-driving car in the real world, while the real world is very complicated, the car itself perceives the world in a variety of ways and doesn't necessarily just feed a high definition, full color image of the surrounds into its own machine learning systems. So what you would typically do in a video game is you would mimic that behavior and when you mount a camera on a virtual camera on your virtual car, the signal input that's coming from that camera would actually probably be something like a very low resolution black and white sampled image. And you would feed that very low resolution black and white sampled image into your neural net in the game. And then when you build the relevant physical version of the same thing, you would feed a very low resolution black and white image of the real world into your neural net on that side. And because they're very similar when you break it down to a low resolution image, you will get the same result. So I didn't say it in the presentation because it wasn't necessary to explain what was going on, but that car that was driving around the colorful track, the image input it had to drive was actually 32 pixels by 16 pixels black and white. So it effectively reduces the world to a very pixelated thing that is very quick to train a convolutional neural network on for image understanding and recognition. And that makes it simple. But also lots of real world sensors, things like LiDARs and measuring distance and stuff is very easy to replicate in a simulation engine, which means you can pretty much supply exactly the same data as your observations from in your game engine as you would get in the real world.
So you say the trick is we simplify reality and then everything works.
Yeah.
And what's your opinion on this kind of simulations that are based instead on very high resolution scenarios? For instance, having a LiDAR that tracks everything. Do you think that can be ever used?
You can absolutely do that, but it relies on a better understanding of the domain. So I am not like an expert on LiDAR. I'm not an expert on self-driving cars. If I was going to build something like that in a simulation, I'd want somebody who could precisely give me an understanding of the parameters of a LiDAR so I could replicate it. But it's absolutely capable of it.
Yeah. I mean, the Tesla team agrees with you that we have to simplify things, so maybe there is no need to learn about LiDARs. Okay, Paris, this was very, very much fun. Thank you so much for coming with